sampling and how to generate probabilities based on samples. So basically, chapter 8 is a lot like chapter 7, except the only difference is when you do problems, you will see we are dealing with a sample instead of population data, as in chapter 7, normally distributed variables. So these are some of the stuff that we are covering in chapter 8 here. Yes, there it is. A sample. Why do we sample from the whole population? So basically, these are some of the things we may have covered in chapter 1, talking about samples, and we are going to specifically focus on different techniques or ways or methods of sampling, define what is sampling error, find out a sampling distribution, so that it's almost like not just talking about the population distributions as in chapter 6 or 7, but going over samples and sampling distribution. And as you increase the number of observations, the sampling distribution can approximate the population distribution with the same mean and standard deviation, as we used to standardize Z for our normally distributed variables. We can show these through the central limit theorem. As your number of samples become larger and larger, or you take larger number of observations, your sampling distribution approximate the population distribution with some mean and standard deviation. So basically, towards the end, we will review problems as we have done chapter 7 problems in the same manner. We will also do chapter 8 problems, except here we will invoke the sampling rule. How to first find out that there is a sampling distribution going on, and so what kind of distribution we are into, and then find out the probabilities based on that. So the problem section we will check up in a separate video. In the first video here on chapter 8, I will focus on sampling and the rules of central limit theorem. So why do we sample from a population? That's pretty basic to understand. Why would we sample? Why does the census sample? Why would you sample or survey people if you're doing some project or some research? Why would you sample people if you are working with a marketing company and you need to actually find out whether your product will sell or not? It's basically the impossibility of using the whole population. So for example, if you were working in your marketing company and you are asked to find out whether this new product would be a likable product, let's say new perfume or brand of perfume that you're launching, and it would be used by people, you're not going to survey all men and women, but probably a group of women at a certain age group who will be using perfumes. You will sample those women and launch your product based on the results from that sample. So it's basically the impossibility of surveying the population. It's not just the impossibility, it's time consuming. And it's also, as we all know, this is very expensive too. The sample results, given how much observations you have provided in your samples or how many you have sampled, would be a very good approximation or an estimate of how much the population estimate would be. So sampling estimate is always a good approximation. A probability sample is a sample selected such that each item or person is as the equal likelihood. So it's almost like the classical theory of probability, which we covered in chapter 5. We said that everyone, the number of favorable outcomes divided by the total number of outcomes is the probability of getting that outcome. So it's almost like that. You're sampling and everyone has an equal likelihood of being in the sample. This is the best method of using the sample because you're not kind of ignoring anyone, and which might create bias in your sampling. So some of the commonly used method of sample, the simple random sampling is just a mirror image of what we just discussed in the probability sampling, that everyone has the equal likelihood of being included in the sample. Best representation would be not our perfume launching example, because you're probably kind of doing some other sampling of women who are using perfume, but a very good example of a simple random sample would be just taking a sampling of students to figure out how much would be would be the score from statistics exams and assignments of the last 10 years, sampling students from a population of students at Northeastern State University to understand what majors they opt for, etc., etc. So basically, every student has an equal likelihood of being included in the sample. So this is another way of random sampling. Random sampling has ways and manners you can always download from internet. There used to be a time where we would use in statistics real big statistical handbooks, which would go through the random number dialing or random numbers like these, and every fourth number you select from there. So this is a very good way of using these when you're doing telephone surveys. Yeah, and I've read some theses which are using this kind of sampling. They would just have a random numbers like these in their handbook, and then they would dial people. Every fourth number coming up, they would dial, and they would say, well, this is the random way of doing these. Or sometimes you do this random numbers too, as you can see. You've the third employee from this set, fourth employee from this set. So you're kind of putting some kind of randomness, and there are lots of ways you can sample through this method. Systematic random sampling. Systematic random sampling is, it's almost like the items individuals have like this, you have 845 employees, and you are staking the individual is some kth member of the population. It's kind of like these. Okay, so you wanted to get a sample from a 752 and number of observations is 845. Let's say this is just a hypothetical example. K is the number of observations divided by the number of samples. If you remember, we had used big N as a population and that's your number of observations. And so small n becomes samples, small n becomes sample data. So the number of observations in the sample. So you are getting this kth unit from your data, from your 845 data to select the first sample, and so on and so forth. The more common methodologies for sampling would be the stratified sampling and the block sampling or the cluster sampling. The stratified random sampling is very interesting. This is what you may use if I was doing that example of launching a perfume based on women's tests. You might want to do a stratified one given what level of income or what kind of populations, for example, women and this age group were using perfumes. Very clearly, the United States Census would sometimes strata or use stratified sampling. More often, it's the block of the census tract sampling, but sometimes it's depending on income level, there would be the stratified random sampling. So for example, this particular company wants to determine whether farms with high returns on equity spend more of each sales dollars in advertising than farms with a low return or deficit. So basically, you want to put some strata on farms based on their returns or on equity, or what is the profitability measure. In many statistical examples, returns on equity is a very good indicator of profitability measure. So you are sampling them 30% and over equity returns. So those are very low depending on the number of farms who have been sampled. That's just number sampled is 1 because only 8 number of farms out of 352, 30% and over, whereas 10 to 20% had of return on equity, there were 189 or almost 200 farms out of 352. So we are going to sample more of these. So we might say it creates sometimes bias. You're sampling more of those which have the higher returns to equity, but that's what is needed in this kind of project. We want to see whether the farms which have the higher level of equity are spending more on advertising dollars. So that's what we want to see. So for example, another project would be whether high-income neighborhoods have purchased homes which are closer to a good school districts or something like this. So we would sample houses which are in the high income neighborhood. So you would have relative frequency on, relative frequency is just our probability. So you'd have the high relative frequencies of houses which are clustered near the good school districts, so that you get into those neighborhoods, find out you get into those neighborhoods which are the high income neighborhoods, and then you sample more of the high income neighborhoods houses and then find out the correlation with the school districts. So if the high income neighborhood houses are near the good school districts, then probably that's creating a policy that the low income neighborhoods are not getting the good school districts, and maybe that's affecting the education in the low-income neighborhoods. So there's something for policy to talk about these. So we want to complete the research, and we want to see if indeed the high-income neighborhood houses are having the better school districts. And if that is true, something must be done by the government. So that's why sometimes we need to have stratified random sampling. That's my example. There are other examples we can always talk about, but that's just one example, and this is the textbook example I'm representing here. So you are stratifying your data based on where the likelihood is more, and then making a correlation out of that. Now, I was just telling you the fourth kind of methodology of sampling, or the kind of sampling would be the cluster sampling or block sampling, which is often used by the United States Census Bureau to find out, or to determine some of the things that they're doing. So census collects data on income levels, on demographics, on income levels and economic, socioeconomic data too, that includes things like marriages, divorces, etc. So all these are done through cluster sampling. Every census has tracts or blocks and divide, and then you have clusters of population living in those. And then when you create those geographic boundaries, you collect sample by randomly selecting from those kind of clusters or blocks. So census has tracts. Tracts consist of blocks, and then you do the cluster sampling from those blocks. There is this essential reason you can see why we do these in U.S. Census, because if you ask a census person or researcher what purpose those data would serve, and I have used some of these American Community Survey data from the U.S. Census. Those kind of data actually serve the purpose of understanding in which part of the United States at the local level, right from regional Oklahoma to the local level, you can go from towns to small cities, smaller towns, and understand what kind of data you can generate at that local level. So we can have data from Tahlequah, we can have data from Broken Arrow, as well as we can have data from Oklahoma and for the whole United States, and from the metropolitan region of Oklahoma City and Tulsa. So that's why, ladies and gentlemen, it's very important to understand the types of sampling and when and what method we are going to use. So that really concludes our methods of sampling. Now, the next objective is to move on to what we call and this is one way of cluster sampling, as you can see, random regions and then sampling from those regions. Then we move on to sampling and the difference with population. So since we are sampling, we said that it's highly expensive to take the whole population data, and we know that we have methodologies to collect samples. We do have some sampling errors. Our goal, ladies and gentlemen, is always to minimize the sampling error. So we would know that there is an error between the population estimate and the sampling estimate. So we know that this error we are creating, and we will try to minimize that error and have the best estimate. A sampling error is the difference between a sampling statistic and its corresponding population parameter. So a population parameter would be, say, the mean of the population, the mu. Okay, so population parameter samples mean, or the Greek letter mu, samples. standard deviation or sigma. Okay. We have a population number of observations in, okay, whereas a sample statistic, or all these statistics would be, examples would be sample mean, excuse me, if you recall, in chapter 3, we had used some of these sample means, and we had divided the sample data, the sample number of sum by number of observations, taking the sum and divided by n-1. I told you, you lose 1 degree of freedom. So that's the thing with sample mean, which is x bar, which is different from the population, meaning population data, you're not losing degrees of freedom. Sample, you're estimating losing degrees of freedom. We call it a sample statistics. A sample statistic, unlike a population parameter, which we call a sample mean, sample standard deviation, or it's called, I think it's sigma, it's S, small s, just a small s. Okay, things like this. And we know the sample number of observations, we call it small n and not big N. Then you have the S squared, and so S squared would be the sample variance, and sigma squared would be the sample population variance. So basically, the difference, the divergence between your sample estimate or sample statistic and the population parameter would be a sampling error, which we are trying to minimize. Our whole objective in statistics is when we get an estimate, we want to minimize these sampling errors. And it would be a mess to see how many methods statistics and econometrics have devised over the decades to minimize the sampling error and arrive at unbiased estimates. So sampling distribution of the sampling mean, and this is where we will gradually invoke the central limit theorem. The sampling distribution of the sample mean is the probability distribution consisting of all possible samples of a given sample size selected from a population. Now you're doing the actual work. From all those methods or types of sampling that we saw, now we are applying our sampling knowledge. We are going to sample from hourly earnings from these data given to us. What is the population mean? What is the sampling distribution of the sample mean? So basically, we have 7 employees working here. So let's see, the population mean, of course, is the population earning 7, 8 plus 8 plus 7 plus 8 plus 9 divided by 7. That's straightforward. But if you want to do samples of employees and see what kind of estimate we get, is it close to the population mean estimate, we have to sample from this population of even 7 employees. Mind you, this is a hypothetical example. Usually populations will have hundreds or thousands of employees. So if we do the combination rule, it's 7C2, we call it. We are picking out 2 numbers, 2 combinations out of 7. So 7C2, we have 21 possible observations that we can do in terms of samples. So hourly earnings of 21 possible combinations of employees. And we do these sample means, the number of means, which is sample mean of 7. How many is how many are there? Sample mean 7 plus 7 divided by 2. So when are you coming to the sample mean of 7? So how many are there? Number of means 3. 7.50, number of means 9. Okay, after doing the sample means, where is 7.50, and you have 9 such observations of sample means or frequencies. 6, 3, so 21, all possible number of means or frequency. The frequency distribution, the relative frequency is the probability. So doing the relative frequency or getting the probabilities, number of observations for each sample divided by the total number. And so that's your probability. So what we do is 7 plus 7.5, all sample means. So 7.50, 8 plus 8.50, excuse me, divided by 21, which is very, very close to our population mean. Okay, because remember, this is this distribution was almost like the population distribution. You really did not have to sample it. The population mean would have been a good estimate here. You did have just 7 employees as such. But if you compare the distributions, the spread in the distribution of the sample mean is less than the spread in the population values. That means it's much more concentrated here, okay? No modes like this population distribution, but it's much more, the frequency is higher on one here. Not bell-shaped as such, but approximately bell-shaped. As the size of the sample is increased, the spread of the distribution of the sample mean becomes smaller. The spread becomes smaller and smaller and start approximating the population mean. The shape of the sampling distribution of sample mean and the shape of the frequency distribution of the population values are different. The distribution of the sample means tends to be more bell-shaped and to approximate the normal probability distribution. As I was saying, it's not exactly like bell-shaped, but it's more approximation of the normal distribution. And therein we revoke the central limit theorem. We say that if all samples of a particular size are selected from any population, sampling distribution of sample mean is approximately a normally distributed mean. This approximation improves with larger samples. So for example, if you take more and more samples from the population data, not just we took 21, but you take large population of thousands of people, like 500,000, keep on taking hundreds of samples from there. If it requires statistically 30 samples or more, but I would say take 50 or more, go bigger and bigger, the number of observations in your sample would start approximating a normal distribution. It has been proved through simulated data. See how they have bigger tails or more of left tail or more of right tail. But as you go higher and higher in equals 30, you go into a more bell-shaped, normally distributed data. This is one example, a big paragraph here I'm not reading out, but it's more like taking more and more data from your sample and coming on to the normal approximation. And with that, I would conclude for today. We will move on to other more rigorous explanation of the sampling error we face as we approximate through samples, how to minimize these error, what kind of distributions we use when you're using sampling distribution, not so much important for this chapter, but for the next chapter as it is, and then we will solve more problems. Before I wrap up though, this is one thing that we will be using a lot, the standard error of the mean, which is different from our population standard deviation. The standard error of the mean would be the population mean divided by the root of the number of samples. There will be less dispersion in the sampling distribution of the sample mean than in the population because of these deviation out here. Though as n is increasing, the standard error of the mean will keep on decreasing. So that is why follow the central limit theorem of having large number of samples, data taken as far as possible. So if you are targeting a population of 500,000, have hundreds of sampling to do from, hundreds of surveys to do from your population data. So in the next video, we will carry on doing problems from chapter 8.